Are you enjoying CppCon so far? We're at the midpoint of the week. Are you having a good time? Yeah, good. And thanks, Jimmy and the band. We love having you here every year. This talk is a bit demo heavy, so wish us luck. But first, I want to thank so many people, starting with the bigger picture, Dan Katz of Bloomberg, now Adobe, and all sorts of other folks, including many not shown on this slide, who have worked over the past decade, and Dan especially in the last 2 years, to push this over the line so that we actually have reflection in draft standard C++ for the first time in history as of just 3 short months ago. With anybody who has ever contributed in any way as a paper, as an implementer, but even in reflector discussion, would you please stand up if you have ever participated in any of that? Can we give a hand for all these people? Thank you. Also, you may have gone to Barry's talk on reflection already on Monday. Inbal's got another talk. There are at least 4 reflection talks. This talk is all about what can we do, because when we voted reflection into the standard, the committee allowed me to pause them for a minute just to say, this is a big deal, and it is going to take us a decade to learn everything we can do with what we just added to the standard. This talk is to give us a survey to fire up our imaginations with a breadth of examples. So if one resonates with you, great. Do not try to remember all of them. The slides will be available. The point is the breadth. But let's start off with a few tools. This is the summary of what's in reflection. So the short definition of reflection is the program can see and generate itself. Usually I'll say reflection for both parts, but sometimes we say reflection for the reading part and generation for the writing part. Hence, metaprogram, programs that manipulate programs. To my knowledge, there is nothing like C++ reflection that we just added in any commercial language. It is best in class. And this is version 1. We're going to keep building on it post C++26, but even version 1 is rich. If you have used reflection in other languages, it's great. I am not dissing that. They have paved the way and they've shown how useful reflection is. But this is not runtime reflection. This is static compile time reflection. Of course, if you compute something and want to store it at runtime, you get 0 overhead by default, but if you want to store something at runtime, use the tools that are now starting with define static array, define static string. That's your conversion function to a runtime piece of data. Here is your first Godbolt link. I won't show it to you because there's so many more Godbolt links and others. But this gives you an idea that this is just C++ running at compile time. And we have just a few extensions. So in addition to the for loop, there's a template for loop. And like always, template implies compile time. It also means stamping out loop bodies. So you know when you instantiate a template, each specialization is basically stamped out, and you could get different types and different overload resolution in the bodies. Think of that for loops, because you actually want that, but it's actually easy to use. Of course, if you do that, you'll probably want a constexpr, a function over what you're iterating, a data member over what you're iterating over. And then you have the double caret, or the cat's ears reflection operator to reflect on the type. And here's a little example that simply takes a type and iterates over its members, which we've never been able to do before, and simply prints out their names. I want to address an elephant in the room. How many of you are concerned already, before reflection, about compile times? I don't see too many hands that aren't up. Okay. How many of you are afraid of all this talk about compile times tomfoolery? Yes. The answer is on the slide. We are about to see a huge explosion in C++ compile time code. And it's generally going to make your programs faster, your builds faster. Here's why. Because it's not just adding stuff. If you're doing something new, of course, you're going to get the added cost. But if you're replacing something you're doing with template metaprogramming today, how many of you have already, just with the constexpr functions we already have, how many of you have had the experience of taking something you have computed by template metaprogramming changed it to const per code, which is more readable and debuggable because it's just code, and found that it's an order of magnitude faster to compile. Quite a few hands. That's because you're expressing your intent directly. Instead of expressing computation through a type system and specialization that was never designed to compute anything, it was an accidental side effect that it was Turing complete. Instead, you're expressing yourself as code, and guess what? Optimizers love code. They see code, they just automatically latch onto it and optimize it. Debuggers work, and this is a benefit, and this is why we already see a speed up from using const per code. The same thing with extra side compilers we'll talk about. When we simplify our tool chains and do more in the compiler instead of repeating mostly maybe right parsing, we can get rid of all that, faster builds. So we're going to do quite a few demos. Wish us luck. And I'll keep saying that because the demo demons are always nearby. But I'm going to show 3 implementations. The first 2 are Dan Katz's Clang implementation and David van der Voorde's EDG-based implementation of what's in the draft standard now, plus some of them will see a couple of extensions because they have a superset of what's in the standard. And I'm going to show examples that are in C++26, but I'm also going to show examples of what to expect in the near and medium-term future. For some of those, I'm going to switch to my CppFront compiler, which again is C++. It's a different syntax, but it compiles to 100% portable C++ that runs on every C++ compiler that's been around for the last decade. But its reflection implementation is ahead. So I'm going to need to use it because I've implemented more of reflection in it than we have yet in the prototypes. But it's all coming to the standard. No confusion here. We're talking about the future of C++ itself. So let's start, having looked at the tools, let's start looking at things we can do today. Now, in this section, I'm going to talk about things you can do with just the things that we have added to C++26 as of June. It's so fresh still. After that, we're going to look at things we can do post C++26, but in the nearer term, like that might make C++29, maybe. But then I want to take us beyond and see how can this affect the long-term arc, not just of C++, but of other languages and of our industry. Because we don't get to do that very often by adding a feature to our language. So here's a roadmap sketch. I'll come back to this slide and highlight different parts, because both the reflection, the reading part, and the generation, the writing part, we have a subset now that we've standardized version 1 in C++26. And we're going to add more, but we'll come to that later. But for now, we've added reflection for namespaces, classes. We even got functions and parameters, and something called annotations, which are basically, they look a lot like attributes, but inside the attributes, they start with an equal sign. I'll try to remember to demonstrate one of those. And we have a little bit of generation in the same translation unit with the splice operator, the square bracket colon. But we can generate anything we want as long as it's in a separate file because we have OFStream. We have cout. We know how to send text and binary information to a file. So we don't have generation fully in the same translation unit while we're compiling it yet. That's coming. We can do quite a lot by just using reflection and producing a file. Here's a warm-up example that uses the feature hash embed and the splice operator. And you'll see the Godbolt link here. Let's actually switch to that. If this works, I'll have a much better chance of the rest of this talk. If the demos don't work, I have the slides. But live demos convince us that it's real, right? So here we have a Godbolt setup with CMake, and it's a multi-file setup. And what we're doing is, the first thing we're doing is we're going and we're creating a JSON data variable we're doing hashtag embed test.json. That's take that file, paste it as if it's here, essentially. Why would you want to do that? Well, you might want to check that file in separately. That file might be the source of truth, not just for my C++ program, but for other parts of the system. So you don't want to copy it, you just want to check it in once. And in fact, here it is down here. We can see that it's a JSON file that has an entry called magic of type string, and then a nested struct, basically. It assesses entries of word of type string and of number of type int. And then we're going to call this function, and I'm not going to step through it. If you want to see the answer, it's the 150 lines above this in this Godbolt example. So you can look through the code. Please do. And what this does is it parses the JSON data that we just embedded up here, and it does something really wonderful. It creates a brand new structure, a data type that is computed, a computed generated data type that matches the runtime input, the compile time input rather, that we just added externally through hash embed. So that we can actually say now v.magic as if it's a data member because it is, v.inner.word as a nested data member because it is, and we get exactly those things printed out just as we would expect. Now, one thing I'm going to point out here, because we have the new reflection operator, the Katz operator, right? I'm going to get in the habit of doing this, I guess, the double caret operator. And we have the splice operator. Some people are wondering, oh, is this all this gunk going to infect my code? It's actually not too bad, at least not yet. But this is the kind of thing that naturally goes in libraries. So here's an example of how you do that. I'm putting this splice here because I want to show you splices, but you can just as well say, call a regular template, in this case, a variable template. So now the call site is just like we would expect in today's C++. And inside that variable template, we are doing the splice. And it could be a function template. So you could hide the reflection operator inside a function template as well. So that's the kind of thing you can do. If you don't have to make your users know about reflection or splicing. You can put these in libraries because it's just code. One last thing, because why not? Because we can. We also have this static assert, but I want to walk you through what this does. This is a raw string literal, which basically prints some information and validates that it's prints some information that's in JSON format. So this is JSON right here. We then use a user-defined literal, which C++ already supports, which converts this to an object. But because it can use reflection, that user-defined literal invokes the reflection, creates the struct, and we can immediately use the member of the struct, of this computed generated type. So that's kind of nice, and it gives us a warm-up as to what we can do. Now let's go to a slightly more advanced example, but it's still simple, so we can go through it in real time. A command line option parser. So we've all used command line option parsers. What this one does that's a bit different is that parse options of myops looks just like an ordinary template call because it is. But notice it's passing the option struct and only the option struct. It's not passing separate string name. If it's this, then fill in this variable with maybe an object pointer. No, it's just saying, here's the struct, go fill it. And just look at the struct. I told you what the flags and names and their types are. Just go fill it. So let's take a look at what this would look like. Here we have that struct, and we can see that, yes, in fact, this works if we have the command line, which I can barely read, yes, count for, has some other stuff on it. It's count 42, and the file name is not specified, so it defaults, and if we just left off file name, it would default as well, because we have a default value for the file name. This is all great. So what is actually going on here? So let's scroll up, and as we scroll up, we'll see that parse options takes its template parameter, and what does it do? The type itself is an input. So we're going to use a template for, which is going to stamp out a visitation of every non-static data member of reflect that type. Now notice here we've put the reflection inside the function template, so it's not leaking out everywhere. Not everybody needs to write double caret. It's up to you where you put it. And then we simply go through. Do we find a command line option that starts with -- that flag name? If so, then what are we going to do? Then we go through and we try to create a string stream and stream that value into opts dot, and then do you see the splice there on line 36? Into opts dot data member. And this is, on one instantiation will be opts dot count, and another instantiation will be opts dot fname. And the types will be right. You can see why we're stamping it out like a template, because the types are actually different in each loop body potentially. This is type safe, and all we did is iterate over the members, search for their names, oh look, a name matched, and then try to stream into that. It's all type safe and correct. In fact, if here I had tried to say count x42, oh, error, value supplied for dash dash count is not a valid int, and we got that message because we actually displayed the nice name. Even though the compiler might have put I as the type ID.name, we're going through all that and we're saying, give us the real honest to goodness source name, display string of the type of that data member. So you're not getting the mangling and coding, it's the actual source type that the user can understand. So just to prove some more that this is live, let's add another data member, another thing that we could add. And once the compilation catches up, there we go. We still want to fix our count value to be correct. But now let's say we want to put, oh, look, now ops.pi defaults to 3.14159, as it should. You know, it's a float. Like, do not give me grief over using a float for pi, even because it's about to get worse. Let's say we were in Indiana in 1897, and we say pi equals 3.2. Oh, did I type it correctly? It's so small that I can't see. Anybody see if I made a typo? Oh, there's no equals, that's right. There we go. Now we conform to what almost passed legally in Indiana in 1897. If you do not believe me, look it up. Came this close, although the Senate spent most of the time laughing at it, which is good. Now here's a longer example. I'm going to do a Mission Impossible kind of riff and call it Mission Drawable. We want a drawable type erased wrapper that will wrap any object that has a draw function that can take a coordinate or something convertible to a coordinate, and that returns an int or something that can be converted to an int. So if you think about the conversions on parameter and return, this is just like std function does. So it doesn't have to be exactly this, but it has to be compatible with that interface. And because I hadn't written one of those before, I thought, let's see how good an AI is. And I asked ChatGPT to do it. And it wrote 200 lines of code, which I then tweaked. And I don't pretend to understand all of it, but it seems to distinguish between const and non-const. Those of you who've done this will tell me whether it's right. It appears to work. I tested it, and I tweaked it. And now, yes, in fact, you can have a vector of drawable and put in a sprite, an icon, a button. Those are three unrelated types right here, and put them in, and then call draw polymorphically on each of them, and it works. How do you do this? What's the core data structure inside drawable? Somebody yell it out. vtable, yes. This is called how you write your own vtable. Let's see what ChatGPT, with a little assist from me, did. I'm not going to go through all the lines. This is over 200 lines of code. But here I want to just prove to you at first that, in fact, there's nothing up my sleeve. Is that big enough for people in the middle and the back to kind of see? Yeah, OK. Oh, even at the back. OK. I want your vision. I'm so jealous. OK, so we're doing this vector of drawable. Let me page up just to prove to you that, in fact, we have sprite, icon, and button are all unrelated types, no inheritance up our sleeves. And in fact, some of them have the exact function that we're looking for. In this case of button, it takes a point, but a point can be, that we see right above it, can be converted from a coordinate argument, and it returns a short, which can be converted to an int. And all of these are compatible, and they work. And you've probably seen demos like this before. Here, let me pull this over so you can actually see that, in fact, yes, on GCC, on Clang, on Microsoft, all of this works correctly. No reflection here so far. The reason I'm showing you this example is to teach you, and as I was learning it myself, my whole career, I've written about things as I am learning them. That's exactly the same thing here. Now, how do we generalize this? Want the short answer? Get the ordinary case working that you write by hand, cut and paste it and put quotes around everything, and then substitute in the names that you want and put in loops where things vary by, say, member function or data member. It's actually that simple. This whole example end to end took me 2 hours from a standing start, from a blank screen to ChatGPT, to fixing the code, to writing the reflection code. Now, I have written reflection code before, but I was surprised how fast it went. And let me show you what that looks like, because here we have, let me put this code off to one side so that we can now see the reflection code. So first I'm going to show you the output of the reflection code. So the reflection code, well, I'll show you what it's doing at the very bottom here. Maybe I will show you the bottom first. Scroll, 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 scroll. All it's doing is it's taking an exemplar class, drawable, which has the signature we want to wrap. Could be more than one, but for now, let's just one. And we're going to call a compile time function poly that. So I didn't know what to call it, so polymorphic type eraser poly, close enough. And it's going to now take that as input, and we are going to generate essentially the same code as on the right. And I tested it by cutting and pasting it in, and yes, it works. So here's the includes, class drawable, the various concepts that are at the top of the file that we wrote by hand, etc. But as we go to the file on the left, I especially want to draw your attention as one example of how this works to the vtable. So here is the vtable. It's in the middle of the file. You can see how big this is with the scroll bar here. So we're here in the middle of the file. Most of this is class drawable. This is the left-hand side here is the handwritten one. And notice how we hand wrote our vtable. And it's got 2 entries, destructor and copy, which are going to be the same no matter what. No matter what you type erase, this type erase thing needs to construct and copy. So that's not per function, that's just for my type erased wrapper to be copyable. This is the stuff that's per function. And so if I wrapped something with 2 functions, I'd have double the entries here in this part. So let's see how we do this. So the actual, and let me actually first show you that we in fact do generate that. Scroll, scroll, scroll. I think we're getting close. Nope, that's the bottom. And a free function that we generated as well. Okay, somewhere in here is the vtable. Trust me, it's there. It's hard to find. I'll find it again. No, you know what? I really do want to see it because I want to show you how it changes. So stop me when you see the vtable. There it is. There's the vtable. Okay. And notice it generates the same things as we have on the right-hand side, but this is all done, generated, and of course it's not in the same file. It's spitted to another C++ file, which we can then build and use in the same build if we want to, but we have to use it from a different file. We don't have in-source, in-translation unit generation yet. All right, so let's take a look at this code. So if we look at the kind of code we have to write, let's look at the poly function itself. It is a function that simply takes the prototype and returns a string in this case. And you can see it starts by putting quotes around all the things that we have in the other file, includes your dependencies and everything that. Here's your constructor. When you get to some of these things, you see I just copy and paste the file, and then, oh, instead of drawable, wherever I see drawable, I just change global search and replace drawable to quote plus parts.name plus quote. It's pretty easy. And you do that for everything. Now, some things are per member function. So I want to mention something here and why I did it this way. You'll notice so far this function I've showed you is just an ordinary runtime function. It's not even marked const expert. It's just an ordinary runtime function that does string stuff. but I have to call this poly-impl with this, reflect this prototype, and now it's going to use the reflection information, okay? My initial implementation was to put all of this string, including the function we're seeing here, that didn't need to be compile time, to make it also const eval. And in this example, I hit Clang's limit on const eval operations because of all the strings. So you have multiple reasons. I'm sure compilers will increase their limits as we stress them. But you have reasons to do a lot of stuff in normal code and then delegate the parts you need to reflection code. And this is a good example of that, of good hygiene. And if we go for a quick look, here's the function that handles every member and outputs all the things, all the strings, the pieces that I need. All it does is, this is going to be invoked once per member. It goes through the parameters of of that member function, remembers its return type, its arguments, and it generates all those things that we see. Here's a whole bunch of things. These are pieces that are then going to be put in the right places by the end caller that we already saw that assembles them all. And one of the nice things about this is, if we go right back down to the bottom again, is if I now want to make this where we can see it, if I want to now change this and have another function, we'll wait for that to rebuild, and let's look at the new vtable. Now I've got a vtable that has draw and getName. So now I can wrap anything that has not either, but both draw and getName with conversions on parameters and return types. I didn't write any more code. So this is very, very useful and illustrative of the kinds of things that we are going to be able to do. And I really want to emphasize that the handwritten version was 200 lines of code to make drawable work. And now I've got 300 lines of code. That was the handwritten code right there. If you have good eyes, this is your test at the back. Any hands? No, didn't think so. And all of that is now just generated. I've written 300 lines of code, which will do all of this for any type of race thing I ever want, ever. And I never have to write it again. And I can debug it because it's code. And it'll have code generation bugs at first, but it's just code. We'll debug them, and when it works, we ship it. Now, 8 years ago, on this stage, I believe I did the first live demo of Metaclasses, paper P707, which showed how to use reflection to help us generate C++ types more easily, more correctly. And I first showed it on stage as slides at ACCU. Thank you, ACCU. I believe the first demo was here on this stage. And here's a quick refresher example. I've talked about it before, so I'm going to be real quick. The idea is, today we write the boilerplate on the left. What if we could just say, hey, I'm not just writing any class, I am writing an interface, which means I want certain defaults. All functions are pure virtual by default, even if I didn't write it. That's just the default. I automatically get a virtual destructor, even if I didn't write it by hand. I automatically get suppressed copying and move, that kind of thing. Here is what what we can implement today in C++26. We can do it, it just has to go into a separate file, and then we use it from that separate file. And let me show that real quick in Godbolt to show that it's done. And this is where I wanted to remember to show you one more thing. We don't need you. We want you. Here we go. So here we have class widget. We're using it as a prototype, and I'm calling the interface meta function on it. And look, here it's generating everything we saw. I'm not going to step through it. By now, this is an easy example now, because we've seen much harder. What I do want to show you is, hey, what if we actually add another function to that, say float h double? Oh, look, there it appears. Now we've handled that one too, so I'm proving to you this is live. This is in fact reflecting and generating the correct final function, applying the defaults, virtual and pure virtual. But now let's say we went a little bit further. Let's say you are the author of this compile time function interface. And you'd say, boy, wouldn't it be nice if I could give the user a way to say, oh, all my functions except not that one. I don't want that one to be an interface. I'm just making up a straw man example. How would you do that? Well, you can do it in C++26 without any more language features because you can create a custom annotation. Annotations are in the standard. Here's what it looks like. I can just write here in this code, the user can just write equals suppress, and now notice on the right-hand side, G disappeared. Is this magic? Is there a suppress feature I can Google for in the standard itself? No, there's nothing about suppress in the standard. All it is that in this code, as I'm for eaching over all the member functions, I'm actually looking at the annotations and saying, oh, I want to see all the ones that are not special member functions and that don't have the suppress annotation. And what's the suppress annotation? I just made one. It's just a type. That's how easy it is. And now you've written a meta function that you're starting to provide an API for your users to supply information from your end call site into your meta function. And that's pretty useful to know. That, so far, is C++26. What can we do in the future? Where is reflection going? And again, as we go beyond what's here, it's more hypothetical, but there are proposals and implementations already on the table to add to your own translation unit while you're compiling, so that those things that we did already, like the interface, could actually be used within the same translation unit. And this slide here is now possible with the EDG compiler with this Godbolt link, and it will generate exactly this output. And notice the key thing is we're generating this from inside the same file. And this pattern is one you're going to see a lot, where I put my exemplar, my prototype, usually in some subname space, and then I reflect on that. I call a compile time function to reflect on that and do something. Well, often it's to reflect on that and make a modified version of it for me to use. So I stick the original, the incomplete one, in some subname space. I reflect on it and make it as I complete it, the completed version. That's going to be so common that I am proposing, I continue, as of 8 years ago, continue proposing there be a syntax for it. Class paren interface is exactly and only a syntactic sugar for that. I've implemented the same thing in CppFront. It's an alternative syntax that's left to right, but it does exactly the same thing, an interface type, and all of these things, including the EDG compiler on Godbolt right now and CppFront with this example, generate exactly the same C++, honest to goodness, portable, 100% C++ code type that works on every compiler. The compile time stuff may not work on every compiler, but the type that's created will work on every compiler. And there are a bunch of these that I've already implemented. Interface is the first one, but polymorphic base, ordered, value, struct, enum, flag enum. We can use class enum, which simply reflects and makes everything context per functions. Flag enum does the same thing and adds the bitwise operators. We can still use the C language enum for compatibility with C, but going forward, I personally believe that the class paren m syntax, which has been provisionally encouraged by SG7 in the committee as syntax for that 4 lines of code, once we have generation, I don't think we'll ever write a naked class again. Why should we? We'll say what class we're writing. I'm not writing any class, I'm writing an interface. And you know what? Once you do that and you express your intent, you'll also never write equals default and equals delete again to get rid of a function that C++ generated that you didn't want, or to reinstate one that you did something that's suppressed but you really did want, because today we have one meta function for all class types hardwired into the compiler. Because the language guesses what you probably want. But I'm not writing a value type, I'm writing an interface, I'm writing a proxy, I'm writing an async function, I'm writing something else. So I'm just going to read from what I wrote 8 years ago, just the bottom part, of that Metaclasses paper, which is now finally becoming real. I'm just so thrilled. Each subsection, because I showed code, uncompilable at the time, but most of it, but actual code that you intended for each of those things. Each subsection of section 3 is equivalent to a significant language feature that would be a language feature in another language. that would otherwise require its own EWG, evolution paper, and be wired into the language, but here can be expressed as usually a tiny library that can go through the library evolution working group. For example, this paper begins by demonstrating how to implement Java C# interface as 10 lines of C++ const expr code with reflection and get the same expressiveness, elegance, efficiency that you get with the built-in language feature in languages like Java and C#, where they are specified as 20 pages of text for a human compiler writer to go implement. 10-line function, 20 pages of text. That I demonstrated on stage with a live demo 8 years ago. Now we can do it in the draft standard and much more. So reflection is going to help simplify the need for C++ further evolution. We're still going to have language features that reflection doesn't directly affect, but many things that would have been language features we can now do as libraries with reflection, and we can do them well. And that means we can test them and fix them. We have code that's portable right away instead of waiting for your compiler vendors to all implement it. It's faster to deliver on GitHub and package managers, easier to customize, to adapt, to fork. So what can we do with this? We don't know yet. But here's a starter list of ideas. If I generate a C++ file, I can generate a JSON serializer, deserializer for a C++ type. Just an ordinary C++ code as reflection. I can spit C++ code, I can spit Python code, I can spit JavaScript code, and reflect over the structure of a type to write a wrapper for another language. If I can spit a file, I can spit a binary file, such as WinMD binary information that CppCX now, the side compiler, needs to generate for a C++ type. I can customize a class's object layout, say class compressed. How many of you have done this by hand and would like a way to do it without template metaprogramming tomfoolery? Generate unit test functions. Go navigate, just iterate over the namespace, find every function named as a unit test, and generate a function to run them all. Instead of doing it in a Python script, just write it as a few lines of C++ code. Make a class's interface async. So class async might run all of its methods, all of its member function calls on a sender-receiver thread pool, and then the return types of those functions may change from T to future of T. You can already think how to write it. Why? Because you know how to write C++ code. If you can write it, you can automate it. All of this in portable, testable, shareable, standard C++ code. No side compilers, no scripts, no language extensions. And here's a prediction, and I'll owe you all a beer if I'm wrong. Really hoping I'm not wrong, and not just because of the beer. We are now on a direct path to be able to, whether the vendors do it or not, to be able to sunset side compilers and build systems like Qt which have to add information that you can't have in C++ source until now, but can with reflection. To sunset C++ CLI, to sunset C++ CX in the next decade. And I think I should know and be able to say that because I led the design for 2 of those, C++ CLI and C++ CX, and I got so much flack for, why are you extending C++? Are you trying to take over C++ in some proprietary thing? No, it's just we need to bind to .NET, we need to bind to Windows COM, and we couldn't express all the information we needed yet in C++ as it was, which is one reason I've been pushing so hard to try to evangelize reflection as a direction so that I never need, as I said 8 years ago publicly, never need to invent C++ CLI or C++ CX again. And I had ChatGPT fix the emoji. This is the iOS emoji, pretty good, but I think it needed a smile. So thank you, ChatGPT. The key to remember, if you're thinking, what can I do with reflection? Simple answer. If you can write the code by hand, you can write the code to generate it as strings and tokens. So what would you do if you had the equivalent of an accurate, always up-to-date C++ parser available to your code? We are all about to find out. We are all about to find out the answer to that. Now let's look at statements and expressions. That's the next thing, because notice we could do a lot already with namespaces, classes, functions, parameters, annotations. That's a lot already in version 1. Hot on the heels is statements and expressions, and these ones I'll have to show in CppFront because we don't have reflection of those things in the in Dan's or in David's implementations yet. So this is a place where CppFront is out ahead. But I want to show you something called Autodiff. And to do that, I'd like to invite to the stage Max Sagerbaum. Would you like to give him a hand, please?
Thanks for having me. Oh. Thanks for having me.
So I'm glad you could come this year, because last year you were at an Autodiff conference in Chicago the same week as CppCon, giving several talks. That's because Max is a world expert in Autodiff. So it's better for him to present a lot of this material than me, because I would have to fake what I've heard, summarize what I've heard. He knows this stuff, including he's implemented one of the major Autodiff libraries that exist today and knows the trade-offs. So let's talk about what it is, because by now some of you are thinking, you keep using this word Autodiff. So I know about automatic differentiation in Maple, like symbolic differentiation. I remember doing that in school. And I know about numerical, where you make epsilon, you make the delta smaller and smaller to epsilon and do approximation to try to figure out derivatives. What's different here?
So automatic differentiation or algorithmic differentiation is a mathematical theory where you basically assume that you can separate a computer program into small elementary functions. That's basically what a compiler always does. And for each of these simple functions, we know the derivative. And then by applying the chain rule and the directional derivative, we can then produce a mathematical theory that says we can compute the derivative, and that's how we can apply it to computer code.
And this is better, as the slide summarizes, than symbolic and numerical, because symbolic differentiation is accurate, but it explodes, and it's slow, and it doesn't scale. And numerical is computable, but it doesn't scale either, and you get rounding errors and things like that.
Algorithmic differentiation will always get you the numerical precise derivative.
Yes, and by the way, one thing about option 3, it's numerically precise and it's linear time. It's a constant factor more expensive than just running the original function. And the constant factor for forward is like 2 or 3.
2 to 3, yes, and for the reverse mode, it's about 2 to 4.
So show us forward mode with this example. We have y equals sine of x times x squared.
Yes. The first thing we do is separate it into the elementary functions. So we have sine of x, x squared, and then we multiply these two.
So this is basically materializing temporaries.
Yes. So, and afterwards, we can compute the derivatives. The derivative of sine is cosine, very simple. Of x squared, it's 2x. And then we multiply these two together. So the derivative of y with respect to v is u. So we write u times, and then the derivative of dy. So that's it. And the other thing for v, for u.
And one thing that we didn't mention, one of the nice things about this form of automatic differentiation is you can have functions with control flow, branches, loops, that you can't really easily show as a symbolic function, for example.
That's definitely true. Usually you can support it. Some things might be quite difficult, depending on what you use as an automatic differentiation tool, but usually you can support it.
So what if there is more than one input and output? This just is a function from x to y. What if there's more than that?
So the forward mode, if you have just one input, you can have as many outputs as you want. You just compute it once, and then you have the full gradient of the output. So but when it's the other way around, when you have, for example, in training of an AI model or so, you have billions of inputs and just usually one output. So then you would have to run this 1 billion times, and this will take some time. You can cut this off by constant factor if you use a vector mode. But if you use reverse mode, you can just say, OK, I run this once, store some data, and then I reuse what I have stored and run the reverse pass. And then you get the full gradient in one pass with a little bit of memory overhead, what you need to store. But usually this you can manage.
So forward mode is good when there's fewer inputs than outputs, and it's linear. I got that direction right?
Yes, that's correct.
But that wouldn't scale. You have to do a million of those if you have a billion inputs. Then you want reverse mode, where you take a pass through, you do a forward pass that calculates the data structure that you then navigate backwards, but it's linear, and then you get all your derivatives even for your billion inputs, still linearly.
At once, yes.
Yes. Now, what if you want the second derivative, the third, the nth derivative?
So the nice thing about algorithmic differentiation is you have a code, you apply it, you get a different code. Then you can apply it again and again and again, and you can have arbitrary high derivatives. But the problem is, usually that's not what you want because it's very general and you get a lot of derivative values or derivative directions you have to specify. What you can do is to have a Taylor implementation and then use this Taylor implementation that will reduce the number of values you have and the number of directions you need to specify. And in 90% of the cases, that's what you want to have.
The summary, I would say, of that, the big takeaway is, it's just code. You have your whiteboard discussions about how to optimize it. It's just code. So why should we care? Does this come up in any important fields?
So we have heard about this a little bit in this conference. It's used for training AIs. So if you have heard about backpropagation, that's basically the reverse mode of algorithmic differentiation. And scientific software uses this a lot also. And yeah.
But you could write these derivatives by hand. In fact, you were telling me that these days people do write the derivative code by hand.
Yes, it's still done. And I have to be frank, that's the best way you can do it. If you want to have the fastest derivatives, that's how you should do it. But your primal code takes a year to develop, and then it takes another year to write the derivative code, or even 2 years, because usually it's more complex. And then the maintenance aspect. You change something in your primal code, then you have to update your derivative code in order to be the same or to compute the same thing. With algorithmic differentiation, there's an initial cost that you have to apply, and then you can run AD in a second on your code, and you have the derivatives. That will not be optimal. But then you can analyze your derivative evaluation or computation, have the hotspot, and then optimize this just one hotspot, and then you will have a nearly optimal derivative computation. One thing for hotspot is a linear system solver. You don't want to do this in black box mode because it can produce wrong derivatives. And that's very easy to optimize.
So right now we have operator overloading libraries, which have limitations. By the way, CppCon is yours. That's what the one that you're involved with. There are custom compilers and forks like Tapenade and Clang and Clad, based on Clang. But as you say, the problem is, if you have like something that's a bespoke compiler, how are you going to adopt that in production? I'm using GCC, and I'm not going to adopt your fork of Clang, even if I am using Clang. I need something production quality. So how would you summarize the benefit, now that you have actually written in CppFront and Cpp2, you've written Autodiff, and you've done it as a library, what's it feel like? What's the difference?
So that's what you already told in your talk. We have now an up-to-date CPP parser at your hands, or a CPP reflection parser at your hands. You have an up-to-date thing, and the nice thing, if you have a nice API, you always know how to query the next thing. You know I have a function. From a function, I know, okay, I can query the input parameters. I can query the output values. I can then query, for AD, the body, the statements of the body, and then the expressions for each statement. Hopefully in CPP29, but knowing the thing you want to query and how to query is the most important thing. That's usually what's the problem when you traverse the AST of some compiler. That's not done for reflections, that's done for compiling. So you have a lot of additional things you then need to ignore, and that makes it sometimes quite complicated to find the stuff you want.
So would you like to see some examples? Here's one. Let's do a very simple y equals x squared, and let's ask the demo gods for their patience and understanding. And so here we have, again, this is CPP2 code, but this compiles fully to C++. It's fully C++ compatible. I'm using this because I have statement and expression reflection here. So here's our function, y equals x squared. We're going to do a first order derivative. And just to show how this works, I'm going to try to run a graph that's visualizer that, once again, ChatGPT helped me write because I am not a Python expert. And where is it? Oh, this happened before when I was rehearsing. I may need to, pardon me, I may need to close the bash shell. Oops. Close the bash shell, close the windows, yeah, close all of those. And let's try restarting them. Oh, here we go. Okay, the first thing we have oh no, I don't want the power. Oh no, it brought it all back. Well, maybe that was enough. Do you think it might have restarted it? Let's see. Oh. Okay.
CH.
I can show you the screenshots, but I really want to show it live. We'll try. Oh, not PowerShell. That's the default.
You misspelled Python.
I'm going to try it one more time. Nope, I'm just going to have to show you this as slides. I'm sorry. But I will show you the Autodiff code. All right, so here we are in demo. So I just won't be able to visualize. I like visual output, and we don't have graphics in C++ yet. Don't get me started. And here we're going to go and compile this code, ad0.cpp2, because all our demo numbers start from 0. And I also am using the print function, meta function, which says, okay, autodiff it, then print the results so we can visually see the code that was generated, and again in CppC2 syntax. So here is the original code. And so tell us what we're seeing here with the autodiff code.
So we added the extra suffix to the autodiff code that we generated, _d. And that's also what we added to the arguments that we have, x. We generate the direction of x, xd, and for the output. And as you can see here, we have the simple multiplication, and we added before the simple multiplication the update for the direction of y. And that's just the multiplication we have seen on the slides before. So that's very simple. And that's when you implement automatic differentiation, always do the derivative computation first, because if you have self-assignment, then you would use already the new value if you do it afterwards.
And if Python was working, you would see this graph in real time for this autodiff example. Excuse me, showing, because all of the source file does is it then says for x equals -10 to 10 in steps of 0.1, create a data file with the values of x, y, and dy, and here they're printed. And this also shows the second derivative because we're going straight to order equals 2. Now, if we do this for another example, let's do y equals x plus sine x plus 10. So here we're going to go to AD2. And let's compile that. So here we see that line 5 is that new function. So we're going to go AD2.cpp2. And tell us what's different here.
So now we have these 3 terms that we want to sum up. And we create the temporary for the second term, which is an expression by itself. So, and we do this first. And that's basically the difference with respect to symbolic differentiation. There you would have to do this all in one thing. That makes it more efficient, or makes AD more efficient. And we drop the last term because it is constant. And that's basically it. Otherwise, we just add here the derivative values.
So notice we have our original function that does what it does. This function does both. It does the original computation, and in the same single path, it has y and dy. Computes them both. So that's important. We're doing it in a single pass with constant overhead. And that looks like this function, where we have the function, the first and the second derivative.
You see here for the first derivative, the linear part drops out, and then for the second derivative, the constant we had for the linear part.
So now let's try one more example. Sine of x times x squared. This is similar to one we talked about before, a slideware, but let's actually see it as code. So here it is, AD3, and we're going to compile that. And again, we've got that function, and it does the same thing, the same basic thing. And now you see it generate something that looks a bit more like an Xbox controller, for those of you who are gamers.
Yes. And
Now, here's a question for you. Now let's add some control flow. Let's take those same three things we just automatically differentiated using reflection, but if x is less than minus 3, we do one of them. Else, if x is less than 3, we'll do the second one. Else, we'll do the third one. What do you think will happen? What graph do you think we'll see? Just shout it out. What will we see on the left-hand side that's below minus 3? The original one, right? And in fact, you are correct. What will we see between minus 3 and plus 3? The second one. And what will we see with x is plus 3? And there's discontinuities. This is a function. It doesn't have to be representable as something you can put into Maple. It can have discontinuities. It's code. But now let's take a look at this in the implementation. And we'll go to 86 because it's 1 plus 2 plus 3. And here I'm going to clear so I can scroll because there's a bit more to show. So let's do CppFront 86. All right, so you're doing two things here. So here's the beginning, and then we do forward mode first. Here's the forward mode.
Yes, and the forward mode for these control structures is usually quite simple. You just need to pull them over into the derivative code, and that's it. That's why forward mode AD tool you can implement usually always, and it usually just works. That's not very complicated.
And now I'm going to show you an example where we need to see both. So here is a function that I learned through you is quite common for testing optimization to see if they can be optimization of solvers to see if they can be fooled. And what is special here about this function?
So we have here loops. We have function calls. This function call we see is differentiated out of context, and then we also have passive values that need to be ignored.
So let's see what this rewank function looks like. And we're going to go through to rewank CPP2. Here we go. So here we see the function. It's got a loop. It's calling another function. That function happens to be non-local. It happens to be somewhere else in the enclosing namespace.
Yeah, let's see if we can handle this.
Well, so are you saying that this function, you're going to do name lookup, find out where it is, and differentiate that one too?
Yes, exactly.
Okay, because it's just code, right? And you can navigate from things you find. So let's see how this was done. We're going to... I didn't really warn you that we'd start going from very simple examples and that there would be a step into the deep end. So there's a bit of code here. Let's scroll back up. So first you've got forward mode here. So here's the original function forward mode.
So forward mode is still simple. The one new thing that we see here is that we have a shadow iterator for the loop because we also need to loop over the directional values. This is C++20 because CppFront is C++20, so there's no zip function available, so I had to do in that way.
All right.
But the other thing is that's what we have seen. There's nothing new here.
And again, we're just computing R and its derivative, and there's a bit more complexity because it's a more complex function, but yeah, we're doing the function calls, and it's not shown here, but there's also the derivative of that function so that we can call it because we're going to call that. Now in reverse mode, that's the second example that's later in the file. We have the same example, but now doing reverse mode, and the only difference is that you invoked the Autodiff meta function and said, oh, do reverse, please. You just changed the parameter. Yes. And now walk us through what you did here.
It's that simple. So we have a different suffix here, and as we see, if we iterate through the thing, that we push some values because R1 and R2 are overwritten here. And when we go into the reverse mode over this again, we need these old values. We need to restore them. And that's what we are seeing here. At the beginning of the first, we go through this in reverse with a reverse view. And then we pop these values that we have pushed at the beginning. As you can see here, we can also optimize this. If the implementer of this has more time, then he might do this. Because we're overwriting here R1 again, we need to push it again. And then when we go through this, you see the code gets a little bit bigger, and that's why the factor for Reverse mode is 4 and not about 3. But this all stays the same. And there we have the external function call, p1 underscore b.
Which is now calling the derivative. It's
Yes.
not p1, it's the one that's going to compute the derivative as well of also that function that we're invoking.
Exactly. And let's see if it's already there. So if we have really generated this.
Great. So,
but we don't have Ubuntu, so we can use grep here.
so
Okay.
8 years ago, when I first gave a talk about reflection and how to use it to write metaclasses, where it was very still abstract and hypothetical, and we had just the very earliest partial implementations where only 2 or 3 examples yet worked, that was still the first time that I know of where we demonstrated on stage authoring C++ classes using reflection. That was 8 years ago. The prototype was written by Andrew Sutton and his team at Lock 3. Thank you very much to Andrew Sutton for that. As far as I know, today was the world's first demonstration of automatic differentiation for C++ using reflection through CppFront, but all of it is directly applicable to extensions to statement and expression reflection added to C++26. So this is a world's first. Thank you for doing that. I understand you wrote 2,400 lines of CPP2 code, and that if you wanted to finish reverse mode, it would be about double that total. So thank you for putting in that effort, and thank you for explaining that to us.
Thanks for having me.
Now let's look a bit further forward. And I want to invoke a really important unsolved industry problem, but to set the stage for it, I want to go back 3,000 years in history to set context that we're not the first to encounter this problem. The Neo-Assyrian, there were several Assyrian empires. One of the latest one, the Neo-Assyrian one, lasted centuries from the 10th to the 7th century BC. Then it was taken over and succeeded by an overlapping but larger Neo-Babylonian empire. This isn't the old Hammurabi original Babylonian empire. This is the Nebuchadnezzar and all those guys. The Neo-Babylonian empire in the 7th to 6th centuries BC. And then the Persians came along. And the Achaemenid Persian Empire lasted, again, hundreds of years, from the 6th century to the 4th century. There were no jet airplanes. This is a huge, huge landmass and sprawling empire. How on earth could humans scale to govern successfully for hundreds of years empires, 3 in a row, of such size? The Assyrians, the Babylonians, the Persians, how did they do it? Well, they had other stuff like roads. But these fine empires are brought to you by the Imperial Aramaic language. And the Imperial Aramaic language was used by the Assyrians, by the Babylonians, by the Greeks. It changed. Imperial Aramaic did evolve. But at any given time, you had a common second language. Not necessarily first, but a common second language for trade, commerce. And also, in this particular case, it was also the language of diplomacy and of government. Those common languages are not always the same, but in this case they were. These empires would not have been possible if the people hadn't been able to talk to each other so easily in such a standardized way. And roads. Well, what happened a bit after that? Well, the Greek Empire was there and then it was gone because Alexander didn't live that long. Again, it immediately fragmented. But we probably all know that the empire that has existed for the longest lived empire in the world, where at least parts of it had lasted till the 15th century, you include the Byzantine Empire, was the Roman Empire, the Roman and the Byzantine Empire. And parts of it lasted till the 5th century AD, parts of the 15th century AD. What held those empires together? More roads, famously. And Latin, especially in the western part of the empire, but Koine Greek was the language of trade. Thank you, Alexander. That because it was so pervasive that people could talk to each other, they could barter, they could communicate, commerce could happen, government could happen. A lingua franca is what binds disparate groups together and makes them governable and usable together. Why on earth am I bringing up ancient history? What is our lingua franca of programming? What if I... You didn't even let me get to the punchline. Everybody's yelling out C, C, right. What is the language? If you want to expose an API that every major language can call, what do you call? What do you write it in? Yeah, we all know the answer, right? It's C. It is the industrial strength duct tape of our civilization. Every API consumable for most languages, operating system APIs, are C. It's our interop glue. What's not so great about that? Type system. What type system? So right, we have, it's low abstraction, and it's also low safety. We can also talk about lifetime memory management. Our whole world, our civilization is built on unencapsulated structs, raw pointers, and manual lifetimes. That is what our civilization is built on. We hear about security problems in C and C++. 90% of them are C. Some are C++, we're working on them, but 90% of them are C. And it's beyond our problem that everybody has to talk this way, including Rust and C# and Go have to talk to each other like that if they're going to talk to each other at all. So you might say, well, isn't the answer certainly obvious? We've had classes since the 1960s. Why don't we just have encapsulated classes and member functions? And what a wonderful idea. And we've done that again and again and again, and nothing has succeeded in taking over the world and solving this problem, to being able to be a lingua franca. Notice I include things like the .NET runtime, and nowadays you might think, well, that's just like C# and F#. Like why would that be a lingua franca? CLR stands for Common Language Runtime. There was a hope in the early days that many languages would be able to interoperate on this platform. That didn't materialize, that it could be a new operating system platform. And we have all these things. I have no hope, exactly zero hope, of this problem being significantly improved for the rest of my career, unless we can do it through C++ reflection. So let's consider this major problem, and let me tell you why I think C++ reflection, even if it doesn't work, nothing will, but why it has a hope and why I think it is our best chance at a solution. Disclaimers, the following slides and demos are proof of concept. They do generate 100% ordinary, portable, standard C++ code, but I'm using CppFront reflection as a proxy because it goes farther than the Clang and EDG implementations do yet. But do please view it as a proxy for looking into the future to see what we can do in real ISO C++ reflection in the future. View it as a prototype proof of concept for that. I am not the first to suggest this. There have been other attempts, including with C++ reflection. Thank you to these paper authors. Callum, I think, is here in the audience. Some of these other authors are too. Dan's name is there again. We have this idea. I am glad people are thinking about this. Let me try to show you why. I would love for there to be a future where I could use reflection to author the class on the right, to just say, instead of class interface or class value or proxy, I could say class Python. One word. Compile it, and have Python just be able to invoke it. Now, let's see if Python is feeling better, because I would love to live demo this, but I have to do it in Python. So we'll try to start Ubuntu one more time. If not, trust me, that code works. Spoiler alert. But I want to show you what it takes to do. And let's see. Try to reboot Ubuntu. Here we are. Let's put you over here. Make you bigger. And we'll go to and let's see. So what I want to show you next, we had the Grewang function. Let me show you a widget function that is widget at Python type. This is the same as what I was showing before, just in CPP2 syntax. I just say, I'm not just writing any class, I'm writing a Python callable class. And I may want to have these three functions, which are pretty much as I showed them on the screen. So now we're going to go and we're going to try invoking this from Python if Python cooperates. Even if it doesn't, I'll show you what we generate. And so this is widget.cpp2. All right, so the cppfront compiler has reflected it, but now it's calling some other things I'll show you in a second to finish generating the Python bindings. And we're done. Now we will have generated a Python callable wrapper. And let's just see if this calling code, so here's a little Python script that imports the widget library we just generated, tries to construct the widget because we've exposed the constructor, pass it 10, and then call some functions. By the way, notice that line 5 uses named parameters. How many of you wish for named parameters? So if we expose our C++ type to Python, at least this one, supports named parameters. Now let's see if Python cooperates. And we're going to write caller, execute caller.py. Yay, it worked. And notice I used the name parameter and everything. All right, how did it work? Well, let me go into showing you what was generated. So in my widget CPP, because I do just generate, cppfront generates 100% vanilla C++ code, portable C++ code that any C++20 compiler can take. You'll notice that in my reflection implementation, I can, in my meta function, request to add include files to the generated output, which I need because I'm going to wrap pybind, and I also want to support STL types like std string, so I have that as well. And then here's my regular widget, as it always is, and that's all generated code from cppfront, all regular C++ code. And I generate a pybind 11 module. I call it widgetlib because the name of the class is widget, so that this is generated. If I'd written gadget, this would be a gadget type, this would be gadgetlib. And of course, you can immediately say, what if I want more than one type in the same Python module? You can immediately think how to write the meta function to do that. Just pass a parameter saying what you want the module to be named, so you can put several of them in the same module. You can all think of the answer because it's just code. It's just code at this point. But notice what I'm doing is I'm saying which class I want, and I'm repeating it also as a string. I am also going and creating the binding for the constructor for the add function with its argument name, with the shout function for it with its argument name. And this generalizes to multiple parameters, as many functions as you like. And as a post-build step, I also, in this case, you could do this with CMake, but the cppfront also executes G++ to build the Python 3 library, and that's what makes it possible. So the next thing you might think is, that sounds like it was useful, but I am a web developer, and I really want to write JavaScript. So then what you can do, let's compile this again, and we compile it again, and this time in widget CPP, you'll notice that we've included emscripten. And this time we've generated bindings. The syntax actually looks a bit similar, but it's very different. This is an emscripten binding for a widget module with the class widget, the constructor, function, and everything. And then we go into the post-build step. The post-build step now is to invoke the emscripten compiler. And now, like we had this working on the slide, we can now have this working, where we just say, oh, I want a class that's accessible from JavaScript. And that code works through emscripten. If you can get emscripten installed, which I was not able to do in time for this talk. Emscripten is huge, or I'm doing it wrong, my goodness. But you can immediately see how, as soon as you run that emc++ line, this will just work, because emscripten works. By the way, we just did 2 languages, right? Because TypeScript is compatible with JavaScript. So we just exposed it to JavaScript and TypeScript. You can do the same with Go. So you can take that widget and say class Golang. and have it be callable with defer w.close, all the normal things you would expect, so expose your destructor as close. I know that you're immediately thinking, oh yeah, here's how I would write the code to do that, because it's just code. We all know how to make a C++ class type available as a flat C API, right? You just stamp out each non-member function and have an explicit this. You have a constructor, a make, and a destroy function, widget make and widget destroy. And this is now callable from C if I want to make class widget, class clang widget. Notice I put the underbar in to avoid any confusion. In the last 2 weeks, Alan Gray at 12D Software decided to try this using the current, not CppFront, using the current reflection prototype by Dan Katz for generating C# wrappers. So we talked about 5 languages, now let's add C#. They have over 5,000 C++ types. And the current tool chain is C++ gets lowered to a generated.i file, it goes through Swig, which is a great library, and then to C#. But there's issues with that. Swig isn't up to date with the latest C++ standard. It can't parse everything. It has trouble with templates, extern template, which they happen to use a lot to instantiate their templates. It doesn't know modules at all, or requires. And also nested classes accessibility. He had to, with Swig, he has to basically if-def private to public only if there's Swig. If Swig, public, so Swig can see it, else private, please, in order to let Swig see the data members because it has trouble with accessibility. He did try C++ CLI, which is really good at this. Right? I designed it, it still works, it's still in high demand, but it's only been updated to work with C++ 20, and he was using post C++ 20 features, and so he couldn't use, at the time, C++ CLI and C++ 23 in the same file, which is what he needed to do. So C++ CLI didn't work. See, this is one of the problems if you do something as a side compiler, you lag. You're always trying to update, and you're always going to be a bit behind. Never mind that you're a side tool that adds complexity to your build environment. So he tried rewriting this in Dan Katz's prototype with Dan's help, so that do not expect this will go as fast unless you can send email to Dan and he will respond quickly. But thank you, Dan, for helping. It took him 3 days to download, install, and get the Clang-based C++ 26 prototype running. And then one very long day and all-nighter, and by the morning light, he was able to parse correctly all examples that had issues in Swig and generate the right things he needed. And here's some of his quotes. He's generating a C++ wrapper prototype. He's transforming std string, std string, in-house text class, a bster, if you know Windows, you know bster and com, into the correct ref string result in C#, the out string result in C#, etc. The most stunning part is we are just sprinkling a few const eval keywords, then doing what we do best, writing C++ code. He continued, he stopped his test there. It's a prototype compiler he was trying out, and he wanted to do the proof of concept to see if he could generate it. Taking this forward, he says, also reflection could generate the unit tests for this, to know the compiler has actually parsed the code correctly and generate the tests for the classes that it just generated to make sure they're correct, the compiler testing it itself. He says, everything points to reflection being able to accomplish what we need, and in a way familiar to every modern C++ programmer. I have lost count. Imagine this in an Australian accent. I won't try. I have lost count of the dodgy C++ parsers I have written over the last 30 years to achieve source code generators. Now, he does add, there are outstanding questions. These are very early prototypes. They have not been upstreamed yet into Clang or GCC trunk. Outstanding questions. How efficiently will reflection handle 50 million lines of code, which he needs to do? Looking good, but now we're talking production scales, boundary cases, integration into tooling and build systems. So we're still going to discover those things. It's only been voted into the draft standard 3 months ago, and yet he was able to get that result already in 4 days with Dan's help for his 5,000 C++ classes he wanted to expose to C#. So if we can do that, if we can expose, just say class Python, class JavaScript, class Golang, class C, and expose it also to Java, to C#, to Rust, to Swift, to Ruby. What would you call that meta function? API seems like a good name for me. I'm writing an API type. And how would you implement API? Well, if you have all the other meta functions, it's just a single 10-liner that invokes one after the other, right? I know if I could know how to build each one, I can compose them very easily. Let's measure compile times. But in principle, this is doable. And if we do that, then instead of the foundation of our civilization being structs and pointers, I'm not saying this is going to happen, but I'm saying our best chance, in my opinion, of if in the lifetime of our careers, getting past C as the lingua franca, is to make C++ using reflection the lingua franca. And that's going to take time, and it's going to take building out. But if we can do that, just maybe, we have a hope for our civilization to build on higher level, safer APIs. Encapsulated strong types, not naked structs. Smart pointers, not raw pointers. Automatic memory management, not malloc and free. At the meeting where we voted this reflection to the standard, a few days before the final vote, because all the reviewing was taking place, was it going to make it so that we could vote it in time? Dan Katz, who authored the Clang implementation, we've talked about him several times. Thank you again, Dan, for all the heavy lifting in the last 2 years. He was talking to Hanna Dusakova, also known as Ms. Konstexper, and chair of the SG7 Compile Time Programming Group, and a co-chair of the Evolution Working Group. Dan went to Hanna and said, all right, reflection, we're going to make it. The review is being done by Core. It's on track to make C++26 this week. And I have to tell you Hanna's answer. So if you know Hanna, or if you've seen her give a great talk, you know she's very reserved, very quiet. Watch out for the quiet ones, in a good way. And very dry humor. Dan said, reflection is on track to make it this week. And Hanna, in her understated way, just gave a little shrug, deadpan said, whole new language. And that's exactly what reflection makes C++. I have one last little confession to make. When I was writing this paper that I first presented here 8 years ago and have been updating since on metaclasses, how to use, hey, reflection's really good, we really need it, and here's how we could use it in particular to generate classes, help us generate classes more reliably, elegantly, simply, simplify C++ a great deal. There's a story behind it, and I'll just, for a minute, tell you the story. In 1957, the Lockheed L-1649 Starliner entered service. Now, this is so early in aviation, its main competitor, you'll see there on the second line, was the Douglas DC-7C. The Douglas DC-7C, just to set expectations here, okay, it was the first commercial passenger jet that could cross the Atlantic westward against the wind profitably and reliably. The reliably part was kind of important for passenger service, although it's not at our current levels of reliability, but we're not likely to lose a passenger this time. That was just a year before it had entered service. The Starliner came out in the next year, 1957, and it was 10% more luxurious. It had 10% more range. It could go all the way from Paris, say, to Buffalo or Chicago instead of just to New York than the Douglas DC-7C. And these were the perfection of the turboprop airplane, but they were getting diminishing returns. In fact, they shipped, these flagship airplanes shipped 1957. 1 year later, 1958, both the Starliner and the DC-7C canceled production. Why? Were they broken? They worked just as well as ever. What happened in 1958? Anybody want to shout it out? Jets. Which one? The Boeing. Boeing was great then. Boeing 707 started production and entered service. It wasn't 10% better. It was 2x better. It had double the speed, could carry double the passengers, and in more comfort. Because if you've been on a turboprop, oh my goodness, you know the noise and vibration. The jet seemed like being in, and our standards have gone up, right? Our expectations have gone up, but this was like sitting in a lounge for people of that time. Like, it was just so much more comfortable and easier and less tiring to use as a passenger on the flight. The 707 replaced all starliners by 1962, and it remained in production for over 20 years. In fact, do you know what year the last 707 passenger aircraft was retired from passenger service? Not freight. It continued longer for freight. It was in passenger service until 2013, the 707. And the fact that we didn't hear about it tells us that they still flew well. The 707 wasn't a blimp, it wasn't a helicopter, it wasn't a submarine. It was the natural continued evolution of the commercial passenger airplane. And it was fully compatible with existing airport runways and existing airport terminals. It celebrated and doubled down what had come before. It didn't try to replace the airliner and say, oh, you shouldn't be using airliners anymore, use blimps now, use submarines now. No, it was just a substantially quantum better airliner, not something else. Still recognizably the same thing, but better in speed, in efficiency, cost, reliability, and yes, user comfort. Jet technology created new headroom to rapidly develop even greater performance and range at lower cost, and it unleashed a new era of aviation expansion. The very next year, in 1959, the DC-8, which replaced the DC-7C, entered service as a commercial jet. The Convair 880 quickly came to there as well. And so back 10 years ago, in 2015 and 2016, when I was first doing my personal experiment that turned into CPP2, to say, how could we refactor C++ to simplify it in ways that C++ itself could benefit from? But is there a way we could simplify it, and how could we do that? One of the things I learned was that the number one way to simplify C++ that I could find was to use reflection, and to assume that there was static reflection in the language. And that would greatly simplify the language itself. We wouldn't need a class, a struct, a union, an enum. We would have those and much more without hardwired type categories in the language, just the general flexible class that can do everything. But I'm writing this kind of class now, and then I'm writing this kind of class, and use reflection to generate those defaults. And that's why I asked John Spicer at the time. We had not had 700 papers yet, but I asked, and he kindly gave me paper number 707. Because I believed then that reflection could be C++'s industry transforming jet engine to accelerate progress while also simplifying our evolution. And I am so grateful for the work of so many people who've done the heavy lifting to make it possible to see it becoming real this year. It's coming true for C++. This is going to be an exciting decade. Reflection has arrived in C++ 26. More is coming. The frontier is open. Let's go. Thank you. Thank you, too. We have time for a few questions. We have mics here and I think here. Please.
Hi. Thank you very much for the talk. I wanted to know, using these reflections for creating these building blocks on top of C++, for adding your very nice wrapper functions to target other languages is a very nice feature. But what do you think in respect to using built module interfaces with a standardized ABI for other languages to target C++, like a Lingua Franca?
So I couldn't hear everything with echo, but I think what you're saying, what about instead of generating wrappers, having a standardized ABI that's cross-language? That would be great if we can get it. Some of the examples that I gave are listed on the screen of attempts that have failed to achieve that. They might have achieved it here and there, but Corba, the .NET CLR, those are kind of attempts to have a standard ABI. One of the problems that you come up with is that languages are so different in their lifetime models. That's why Rust is having such trouble right now interfacing with C++, because their lifetime models are so different. So you do have to have some sort of bridge. The question is, how convenient can we make it? Because right now, the bridging is limited usually to a few types. Like every new language has this problem. They interface with C, they want to use C++ types. They say, look, I've wrapped vector and string for you, but I'm done. You can use all C++. No, you can't. You can use vector and string. So we would like to see if we could do better, and I think that requires assist from the C++ side, because it's the C++ side that has the information, and I think it's the reflection that lets us program it. This is my hope. Hey, it works with PyBind and mscripton, so yes.
Thank you very much.
Please.
So this is a more practical question. With this new fancy reflection, and thank you very much for that, will I be able to take a namespace and descend into all sub-namespaces and process all classes?
Yes.
What would I go around downloading and installing to try that out tonight?
Okay, so you can get the reflection prototype. Search for P2996 is the paper number. That will usually get you to the implementation. You can try it on Godbolt. But yes, my understanding is you can navigate namespaces. But remember, it doesn't go to statements and expressions yet. It doesn't do attributes yet. I think just annotations, which look like attributes, but they have the equal in front. I'm glad they do. But you should be able to go through namespaces, classes, functions, functions, and their parameter lists. That's as far as they've got so far.
Thank you very much.
Please.
I just wanted to make a very, very quick comment about the ABI. So Saksham is around here in this conference, and he have a paper about versioning ABI using reflection. He was actually like did a prototype. Yeah.
Yes, thanks for mentioning that.
Go and catch him and also talk to him, and that's it.
Yeah, but by the way, I started saying this last year. For the next decade, you will not be able to go to a good C++ conference without running into talks about reflection. They're going to be reflection conferences. And there's at least 4 talks at this one, which is great. Oh, yes.
Hi.
I let Inbal slip in, so now let's have you. That's okay.
I'm wondering, are there any plans also to support reflection on free functions? Because I didn't see you are doing that. You're only using struct class.
Yeah,
not
so
free functions.
In this case, I wasn't doing, wasn't showing free functions, but you can reflect over the free functions of a namespace. I'm pretty sure that works today in those prototypes.
Okay, great.
And in C++26. Yes.
In this exciting future reflection-led world, I think we would have a very blurred line between language features and library features. I wonder how you see that, and what would there be left still to develop in the language itself?
So anything that you could compute and patterns you can do by hand today, we often get proposals for a language feature to do that pattern. Those patterns, if you can write the code by hand, you can now write it through reflection. That category of potential language features will very likely be received with, first try to do it as a context per reflection library, and then tell us if it didn't work, right? I'm trying to think of other things. You could probably, it could be that some things could be done as libraries, but might be more elegant as a language feature. So for example, I don't know yet whether named parameters can be done as elegantly, named arguments rather, it can be done as elegantly as a reflection library, so you get the super nice syntax at the call site, or if, because people are very sensitive to their call sites, or if just having to write a couple more characters means, nah, let's have the language feature. So it'll be a trade-off between ability, can I do it as a library? If not, we can still consider a language feature. Can I do it as easily with the same performance, efficiency, and usability and debuggability if I type something wrong as a language feature? If I can, like I can for those meta functions that I've implemented in CppFront, heck yeah, let's make those libraries. And then I don't have to wait for my compiler writer to implement the flag enum type category or things like that.
So that's basically same as today, the same decision whether to put something in the library or in the language.
Well, the same kinds of things apply, but it's definitely not the same as today. Today, there have been proposals for flag enums. And there's been much wringing and gnashing of teeth, like, do we really want to complicate the type system by adding a new kind of type in addition to class struct, enum, union? Now we have flag enum. Now we got to wire that through the type system, through all our compilers, because it's not a class. But with a compile time meta function, you can write flag enum to generate a class with all const expr members of the right things and the bitwise operators. So you see the cppfront implementation for an example of how to do that. Yeah, so then nobody will ever be asking for a flag enum language feature again because we can do that one very well and efficiently and usably as a compile time library. It's a good example, good question.
Hi, so I saw in the examples you gave with the annotated classes that you generated basically a new type from an existing type.
Yes.
Is it possible with reflection in the future to also manipulate the existing type?
So the current reflection it lets you see what's there. It does not let you change what's there, and there's very good reasons for that. The one definition rule gets a lot weaker if you can change the definition. And I think that's actually fine, because the time where you want the hook is to, in those examples, is to generate the rest of the type. So it's okay to put it in a prototype subnamespace and generate the real type. And I think compilers will likely get good at optimizing away the unused originals. In CppFront, I happen to implement it as changing the type that exists, including that if you want to take out members and replace them with something else, like the union and variant types, they can do that. Even there, though, it's conceptually part of the parsing of the type. And once you finish parsing the type, ODR is still sacrosanct. It will never change. So I personally am okay with putting in a hook right before you finalize the type, before anybody can use it, to modify it then. But I think it's only an optimization. And I think it's actually a good idea to not change things that already exist, because now you're going to, if we wanted ABI problems, that's where we would go to invent them.
Yeah, the question was related more to the situation where you have already a library that's maybe defining some types and you want to extend that.
Right, so if you have existing types and you want to extend them, right now my advice to you is generate new types that are supersets of those types, and then see how you can make them substitutable. The benefit here is whatever boilerplate you would have to do by hand to do it, you now no longer need to do once per type. You could write it once and extend all the types as you need them, and just write the meta function once, which would make it a lot more ergonomic and easier, hopefully.
Thank you.
We'll take one more here and one more here, and then grab lunch.
Yeah, so this is really exciting. I know as soon as I tell my manager about it, one of the big concerns will be how long till the tooling catches up. I'm just wondering, would best practices for that gap be maybe using C++26 to generate C++23? Or is there like another sort of, I guess, stopgap while we're...
It's similar. It's actually not so much using C++26 to generate C++23. It's generate more C++26, but generate more code, right? The key is, because we're forced in this mode, in this model, mostly to generate the new code in a separate file, that's actually a good thing. It has the benefit that we can't use it right away, but the benefit is it's code. We can debug it. The step into just works. One of the things that we are going to need more of is const expr debugging. So the idea to be able to step through functions, and we already need that for like when we use const expr code to calculate template arguments, but we don't have it. So what do? We use printf debugging a lot to like, oh, it doesn't calculate the right thing. Okay, we try to run it as non-const expr and debug it that way. We will need visualizers to see the code we generate, and we will need const expr debuggers. And so I was really happy to hear JetBrains announcing a const expr debugger just a few days before this conference. Wow. So I don't know more about it than that headline, but it's on my to read about list because I've been asking for that and saying we're going to need that for the last decade.
Thank you.
One more.
So great talk. Thank you. Always love your insights. Earlier in the talk, you talked about reflection becoming an ability to replace a whole set of language features going forward. So in two parts, how do you have concerns and how do you see that affecting C++, in essence, forking into many kind of distinct and separate languages as individuals create their own libraries? And how do you see these affecting the standardization process going forward? Because now you're just writing code to add language features. Would those move into a separate subgroup? Would they become part of the standard library? What is your longer-term vision for the committee on that process?
It's a great question. I've been answering that question for 8 years, and it's important to keep asking it because now we're actually going to start doing it. Your last words hit the nail on the head when you said, which ones go in the standard library? I can totally see where people say, oh, these metaclass functions, what if I write my interface and you write your interface and they're not compatible? You know what? That's totally fine. We standardize the common ones. They're just libraries. This is no different. This is no different from when Bjarne added classes to C++. Well, not everything's a struct, but I could write my own string class and you could write your own string class. Yeah, that one actually happened a lot, right? But we standardize the common ones. And we have libraries, but you might have your own hash dictionary in mind. Yeah, we standardize the common ones. And you know, when you do make your own, it's not the end of the world. You were able to do that. Good for you. And you're now in a place that you wouldn't have been before. I see these as just being the next meta step there. That's why I called the Metaclasses. All the same answers as for classes. Yeah.
Amazing. Thank you.
Thank you all for coming. Enjoy your lunch and the rest of the conference.